is a pleasure to present Pedro Mendes. Pedro Mendes is professor and director of the Center for Cell Analysis and Modeling, and also a member of the Department of Cell Biology at University of Connecticut School of Medicine. His research interests are in the area of computational systems biology, which aims to better understand biological systems through the use of computer models. He was the author of the popular simulator COPASI, and now the leader of the new COPASI simulator with Ursula Kumar, which will be the main topic of his talk. He was also actively involved in the development of SBML and of the Miriam proposal for model annotation. His other research interests include the modeling of mammalian iron physiology at different scales, the problem of parameter estimation and systems identification, and the area of reverse engineering of biological networks. Over the years, he has worked with people from most areas of science, either in his own research group or as collaborators. Thank you so much, Pedro, for accepting to be here today, and I'm looking forward to your talk.
Thank you very much for the very kind introduction and for inviting me to this workshop, which is becoming very interesting. So just to confirm, you can see my slides, right? Yeah, okay. So I've added a word to my title from what was in the program, which is there highlighted in red. That's just to highlight, because of course there's metabolic modeling means a lot of different things. And in this case, I'm going to focus more on metabolic kinetic modeling. And I'm going to talk essentially about our software, simulation software, COPASI, and not just what it is capable of, but also how it has evolved and how it is being used now by the community. So I'll start with a little bit of history just to put things in context, and then I'll give an overview of COPASI and its user ecosystem, talk a little bit about simulation methods, analysis, and I hope to end with reproducibility, which is becoming a very important topic. So metabolic kinetic modeling has a very long history, in fact, as long as computers have been around. I'm showing here one of the first, perhaps the first digital computer model of metabolic pathway. This is back in 1960, as you can see. Maybe the lettering is a little bit too small, but it's August 1960 that when it was published. This was carried out in one of the very first, I believe at this time, this might have been one of the very few universities that had a computer, University of Pennsylvania, that had a UNIVAC one. That's exactly the one in that image there. And simulation was of glycolysis and respiration in ascites tumor cells. And as you could see, the output was done on a character printer, so very rudimentary methods, but that still allows you to do some kind of interesting simulations and not behavior that is and discover behavior that is not exactly trivial to predict. Obviously, they had many technical problems, and indeed, this paper, if you read it carefully, you'll see that the model really fails to completely match experiments, but still nevertheless allow them to reason about this. So yeah, just to put in context, this is a rather old history of doing this type of kinetic models. Another important milestone as well is was this paper from 1968, so not too long after that first one, which published a generic biosimulator, was called BioSim, by David Garfinkel, and this is essentially was software that would allow you to define your metabolic pathways, the kinetics of the various enzymes, without actually writing a piece of software, without having to write a program. And that has a number of advantages, although in that time still, because computers were not widely available, the outreach could not be very large. But this allows the model specification and the simulation to be independent of the programming language. Models can be manipulated easily. And in fact, this is a precursor towards reproducibility, which I'll touch back at the end. Whereas it is important to make the model independent from the source code, because not just software, but even programming languages come and go. For example, the program that I mentioned in the previous slide was written in a language called, I believe, Fortran. This one here was written in Algol. Fortran is still around. Algol is not really very useful anymore. So if you had written your software, your model based on that particular computer language, it wouldn't be easy to reproduce its results today. So I came back in the scene around the late 80s, early 90s, and I developed a software called COPASI, which stood for General Pathway Simulator. Was exactly the same aims as BioSim had, except that, of course, our computers were a lot more widespread. We already had computers, everybody in their offices in universities, and in fact, we could run simulations on desktop computers. We don't need large mainframes anymore. And so COPASI would allow defining a metabolic pathway based on writing up reactions and just selecting their kinetics from a menu, or eventually typing a kinetic function if it was required. And I already tried to approach the problem of parameter estimation, which I'll again describe later on. Now, moving forward, we now have COPASI. This is kind of the generic slide I normally use to show all of its features. I'm not going to go through these in detail, but just to point out that this is portable software. You can run it on any of the common operating systems. And it, just like COPASI, it allows you to define a metabolic, or in fact, any kind of chemical network in a way that is independent from a computer language. And it also allows you to export it in formats that are standardized and that other software can read and write. But we'll touch those issues in further slides. Now, how did COPASI come around? Well, it was a collaboration that I started with Ursula Kummer way back in 1999. Although our first release of the software only happened in 2006, so it took a number of years to get this going. And even though COPASI completely reused COPASI's backend, so all of the calculations for the simulations were all the same code, but it had a different front end, and it also incorporated Ursula's software for stochastic simulation. So eventually this collaboration continued and is still very actively ongoing. We had several of our students and postdocs came in and went, some of them actually became now PIs themselves. So Stefan Hoops, Jürgen Pahle, Sven Salle, they're all now, they have their own research groups. And we are all still continuing to develop this as a mostly a three-site collaboration. This is kind of a acknowledgement slide, so I should also acknowledge my current funding, which is from the National Institutes of Health. We have a national resource grant on mechanistic modeling of cellular systems, and that's actually in collaboration with the virtual cell software, which is also located here at UConn. So we released COPASI. It's a generic simulator. I'll touch on the features a little bit later. And it's now very well established, has a worldwide user base. And in order to quantify this, which is important for our funding, to justify our funding, but also it turns out to find out about some important things, we now track all the papers that use COPASI, and that I emphasize use. We do actually check if those papers actually utilize the software rather than just mentioning it. So we don't include in this list the ones that just mention it. And so I'm showing here the web page where you can see this in our website. If you just click on research, you get a web page which lists all the papers that we can track, of course, that use COPASI, and it's a long list, as you can see. So if I go back to my slide, so it's over now 1,000 publications already that we have tracked, and that average right now is about 100 papers per year. As you can see here on this curve of papers per year, there was a peak in 2019, which came down in 2020, 2021 is slightly, actually I don't have the updated figure here, but it's more or less flat from 2020, but I think in 2022 the number is coming back up. So I suspect this might have been COVID related, although it's not easy to prove that. And in terms of downloads, we have about 10,000 downloads per year. So it's a fairly sizable piece of software. It's not equivalent to some other software in biology. For example, if you look at packages such as Bioconductor, they have a lot more downloads, they have a lot more users, but then that's also because a lot more people are doing gene expression analysis rather than metabolic or biochemical modeling. So just as a quick thing, as I said, as we collect all of these papers that use COPASI, it was very instructive to us to figure out what it is that our users are doing, and I think that's quite an important thing. So I spent quite a lot of time actually analyzing this, collecting the papers, checking them, many times even saving the models that they have, and figuring out what type of publications there are. And I just highlight that, of course, the majority are journal articles. These are peer-reviewed journal articles, but there's a lot of also theses. So mostly PhD theses, but also masters and even undergraduate theses that we collect that are published, where COPASI was one of the main tools for research. In terms of journals, this is the top 10 journals. It's actually 11 because the number 10 are as a tie. And an interesting thing here to observe, apart from of course, the mega journals such as PLOS ONE and Scientific Reports, because a lot of papers get published in those journals. An interesting thing, of course, there's several systems biology related journals such as BMC Systems Biology or PLOS Computational Biology. But you see also a number of chemical journals such as Journal of American Chemical Society, ACS Catalysis, Organometallics. So it turns out that unknown to us until we did this effort, that COPASI is very widely used in the chemical literature, and really did stun us. It's probably the most used area for COPASI. So people basically doing inorganic or organic chemistry and determining mostly parameters for catalysis. If we look at the topics of the papers that are published, and I'm highlighting here in yellow the topics that might be relevant for this workshop, or that are most relevant for this workshop. As I said, chemistry comes up on top by quite an advance, but then we cover a large number of areas. Signaling and metabolism are the next two, generic biochemical, microbiology. By the way, these topics classification, they are non-exclusive. So there's papers that are on metabolism and microbiology and genetics, perhaps all three at the same time, for example. Also, a number of other computational methods use COPASI either as a metric to compare against, or as one of the tools that they use. So anyway, that's something for us that is very useful, because it allows us to know what it is that the software is being used for, and also allows us to try and focus on those areas. Now, what is COPASI? What can COPASI do? I like using this slide, which shows the cycle of knowledge, of using models for knowledge generation and knowledge synthesis. And so the first thing that you see is that COPASI sits here in this kind of loop that exists, where you have what we call forward modeling, which is probably the type of modeling you most normally think about, where you start from a model and parameter values, and you use a software like COPASI to run simulations, and you obtain some simulated behavior. This is what we call simulations. But COPASI is also very useful for doing what could be called inverse modeling, or parameter estimation, or reverse engineering, where you start from a behavior from experimental measurements, and you combine that with a model behavior, and you try to minimize the distance between these two things. So you go around this cycle a number of times, and that's essentially the effort of doing parameter estimation. So COPASI sits here right in the middle, both in forward modeling and inverse modeling. Of course, knowledge goes through many other ways, feeds back into a model and parameters through all of these arrows, the paler they are, the less well-defined they are, of course. So when we make a model, many times we actually just write things that we know for sure exist. And yet sometimes if we want to track them down, it's not so easy. This is what I call a body of knowledge. The literature feeds into this, but the literature also feeds into databases, and often the literature is what feeds most directly to model parameters. So what are the features that COPASI can mostly do? So the first thing is the basic simulations it can carry out. And it can carry out essentially two types of simulations. Those are time courses. So these are problems where you know the initial state of a system and you want to discover or simulate how the system evolves along time, perhaps in the presence of a number of perturbations. Or you can calculate steady states. So you could do steady state analysis. So steady states here, it's the only one that is different. All the other entries are different methods to calculate time courses. And the important thing in COPASI is that we have three major methods for time courses. The most commonly used is based on differential equations, which is what normal chemical kinetics is based upon. There are also a number of stochastic kinetics methods based on the approach by Gillespie, which is an algorithm that solves the chemical master equation. It solves in a Monte Carlo sense. We have hybrid algorithms that combine ODEs and Gillespie approach, also Gillespie approximate methods such as the tau leaping approach. And more recently, we've added stochastic differential equations. So you now can use differential equations where you add a noise term. The only restriction is that we force the noise term to be added per reaction, not per molecule. And that's in order to be able to continue maintaining mass conservation. If you add noise per chemical species, you run the risk of your conserved masses not being conserved because the noise would be different. So adding it at the level of reactions maintains all of the mass conservation. And then the models can have arbitrary numbers of compartments. The compartment sizes themselves could be dynamic variables, so they could be either have assignments, some algebraic function for their size, or even differential equations. And the models can allow discrete events, that is, interventions that change the values of variables or parameters at given certain conditions. So time course is one of the main methods, basically predicting the behavior of a system a long time. This is a calcium model here running with on the left with the differential equations, and on the right run with stochastic kinetics. And by the way, the COPASI makes it very easy to move from differential equations to the stochastic kinetics. That was one of our original objectives with the software. And of course, you can calculate steady states. Steady states are a little bit more boring. It's not so easy to make plots of steady states. They are essentially sets of concentrations of the different species of your model. By the way, this here is a model of E. coli central metabolism developed by Pierre Millard, who I think it's on the audience as well, which is, I think, still one of the most complete central metabolism kinetic models of E. coli. And also the reaction fluxes expressed here both in extensive and intensive units. So intensive is moles per quantity per time, and intensive is concentration per time. So, but that's just running one simulation. However, when you do modeling, what you want to do is you want to answer in different ways, but you always want to answer this question, which is, how do the parameters affect the state of my system? And those questions can be disguised in many different ways. You might ask, for example, which parameters have the highest effect on a desired outcome. If, for example, you're designing a drug where you may want to have correct the behavior of some signaling or metabolic pathway with a drug intervention. So essentially, you're asking, where should the drug act, or by how much should the drug act? Those are all parameters of a model. You can ask very generic questions, theoretical even, such as what properties of a model are fragile and what properties are robust, being which properties are not really very highly affected by any parameter changes, or which ones are very sensitive to parameter changes. Or you can even look at experimental design asking the question, which parameters do I need accurate estimates for, rather than other parameters that may not need accurate estimates. By the way, this ties up with the question on the biomass reaction, even though that's not really for kinetic models. So all these questions are questions of what happens when I change a parameter, essentially. And COPASI has a number of tools to try to answer this question. For example, we calculate stability analysis of a steady state. So that basically is answering the question, how stable is my system to perturbations on its chemical species, on its variables. We allow sensitivity analysis, which asks the question directly, by how much does a variable change when I change a parameter? And this is done in a linearization approach. By the way, there's two ways of doing this: regular sensitivity analysis and so-called metabolic control analysis, which maybe Emma might touch upon tomorrow, perhaps, in her talk. We allow parameter scanning, where basically you change a parameter value and you run many simulations at different values of that parameter. And we can do this in a combination, several parameters changing, and they can change in regular ways, or they can change with stochastic sampling. We also have optimization, generic optimization, where the user is able to define an objective function and maximize or minimize their objective function, and therefore basically asking the question, which parameter values fulfill this criterion that I want to achieve in this model, given the context of this model. We also have timescale analysis that basically look at how the system, what timescales the system is distributed upon, and we're starting to add periodicity analysis tools, so things to identify periods and frequencies of oscillations, etc. So parameter scanning, that's kind of the most basic one. You change a couple of parameters here in a metabolic model. We're changing the initial concentration of cysteine and the kinetic parameter of threonine synthase. And we can either change these in regular ways and carry out so-called parameter scan, where we trace the steady state concentrations of various things at different values of these two. Or we can do a sampling, stochastic sampling here, random sampling, where the parameters are picked at random between the intervals and simulations carried out. So these two are two expressions of a similar, of the same model, but just done in different ways. The sensitivity analysis, as I said, we have, for example, metabolic control analysis that follows the theory of Caxer and Burns and Heinrich and Rappaport, where we calculate elasticities, flux control coefficients, concentration control coefficients. By the way, you can also scan parameters and then recalculate these. And one of the things perhaps that COPASI is mostly used for, it's the fact that it can do optimization. This is optimization of arbitrary objective functions that are combinations of variables of the model, variables and parameters of the model. And particularly, we have a menu of algorithms to be able to do those optimizations. And these go from traditional type of gradient descent methods, such as the Newton method or Levenberg-Marquardt, but also including methods based on evolution, such as genetic algorithms, evolutionary programming, or other things such as simulated annealing, which is based on physical chemistry. So these are heuristic optimization algorithms that allow you to try to find global optimization solutions. And as I said, there's several of these optimization methods. And then with optimization, we also allow the software to do parameter estimation. That means you feed the software some experimental data that matches some of the variables in your model, and then you try to change a certain set of parameters that is defined by the user within boundaries that the user also defines. And by changing those parameters, the software tries to match the model as much as possible to the data. So here in this example, you have the experimental data being these crosses, and the model behavior being the blue line, which tries to basically fit it. And this is here is basically following the progress of fit as the algorithm moves on, and that's basically the distance of the model to the data. So we want to minimize that distance, obviously. And this is perhaps one of the most used applications for COPASI, as I mentioned in all of those chemistry papers. Most of them are basically calculating kinetic parameters given measurements of reaction progress. Sometimes they do it in an ad hoc way, which they define specific models and they try different models against each other, rather than carrying out parameter estimation explicitly. But quite often this is done, and also in metabolic models and signaling models, etc. So more recently, we have started developing methods to program with COPASI. So COPASI is mostly a front end. Most people who use it because it's has a graphical user interface. It makes it easy to define things and run things without having to remember a language to specify what you want to do with the model. However, a number of users want to write programs around it, and so we have different ways of allowing this. So one is a low-level API, which is used mostly by other software such as Virtual Cell, Cell Designer, and a few Python tools. But more recently, we've developed two toolkits that allow you to very easily write manipulations of COPASI models and running simulations either from the R language through this Cork package. Cork means the COPASI R connector. So you can write programs in R that load the model and carry out an operation. So the operations are carried out in the background through COPASI, but you are instructing it to do it through R. And in fact, you can load several models at the same time in memory and run things and do operations between models, etc. And the same thing for Python, which is also widely used, and that's the Basico toolkit. Both of these are high-level languages, not like here. Here you really have a low-level API very close to the C++. This is much higher level. Most people who can write R or Python can use these two toolkits without having to know much about COPASI. So now I just want to finish by touching upon reproducibility. And so as I mentioned in the beginning with the BioSim, the 1968 software, producing simulators that can read and write standard formats, and particularly now we have SPML, which is a standard way of writing this type of systems biology type models. We have SEDML, which is a standard way, which is still being developed, but it's now already very useful, standard way of describing the simulations themselves and the output that they should produce. These two things together allow us to create a model and specify what to do with it in a way that is independent of the software. So you can do this with COPASI, export the SEDML and SPML, and maybe you want to export it in this OMEX format, which is really just a type of zip file that combines the SPML and the SEDML into one. And then another software can read that and run the same simulation. And there's many different software that can read and write these formats. And in fact, they are now listed in these sites, biosimulators.org and biosimulations.org, which I would encourage you to visit. These are efforts that basically you can load an SPML model on the web, and you can then decide running it on different simulators, and they go back and run on HPC cloud. But the point here is to make is that if you write a model using one of these tools and you export it in a format that is standard and that is standardized, many years later, when the software that was used to create it has already disappeared, people can reuse these models. And one of the things we find out is that models that are written this way are much more often reused, and their papers are more often cited as well. So I would put here a word for reproducibility in modeling and computational modeling. It's as important as it is for experimental manipulations. And so that's just a list of publications of our papers. I don't want to spend any time to this, so I would just like to finish and acknowledge a number of people that passed through my group that worked on COPASI. These were several postdocs, by the way, my groups that have been in different places in Virginia Tech, University of Manchester, and now in Connecticut. Several postdocs, PhD students, master students, even undergraduates that have contributed. I don't have time to mention all of them. My COPASI collaborators, of course, who are partners in crime. More recently now, I have collaborators that are producing the VCell software, which we have joint funding.